Hello everyone. Today we will see few more examples of different statistical tests. We will also discuss the formula once again. So here is one example which we discussed even during visualizations. So these are highest driving speeds recorded by men, and these are highest driving speeds recorded by women. Now we have studied the concept of sampling distribution. What does it mean? So first let me take summary of this entire data. So for men, this is the complete sample. For women, this is the complete sample. So I have 87 observations on males, 102 observations on females. Minimum for males is this, minimum for females is this, and so on. So we have computed minimum, Q1, median, mean, Q3, and maximum. Okay. Now, if I take a subsample of this data of size 30 from males and females each, then these things change. For example, here minimum values were 55 and 30, whereas now minimum values are 60 and 75 for this particular subsample. Okay. Even the means, here the difference was 12 plus around 20 points, 88.4 and 107.4, so 19 points. Whereas now here for females, for this particular subsample, mean has increased, and for males it has decreased, so the difference is less now. If I take another sample, things may be further different. Okay, so this is due to sampling variation. So which sample I take would affect my actual values of mean and median, and here actually I have tried to represent it graphically. So this is suppose range of values for the original sample. Then for subsamples we can have such different ranges. Okay, so the spread could be different in each subsample, and this actually leads to sampling variation. Whenever we want to make any conclusions, we have to make sure that the conclusion is actually justified. Means, suppose I want to say that okay, males drive like the average driving speed for males is higher than females, then we have to actually make sure that this gap is actually statistically significant. This is not just due to this coincidence of choosing a particular sample where we have males who drive at a higher speed. For that we need to have formal tests of hypothesis. So what do tests of hypothesis do? They actually tell us how much difference is needed, minimum how much difference is needed to make sure that this is not purely occurring due to chance, that there is actually a difference. Okay. Now how do we do that? So here is one example. There are two people in this picture. This one is shorter, this one is taller. So this taller person says, my pants are 1 foot longer than his. Okay. And hence I need my hat to be 1 foot wider than his. Okay, so he says that okay, see, I know that my pants are 1 foot longer, so if I use the same theory, then I need my hat to be 1 foot wider than his. Now what would happen if we have hats with those measures? See, a 1 foot wider hat will not work because difference of 1 foot in length is acceptable for pants, but difference of 1 foot in width is not acceptable for hats. Why? Because our heights, range of our heights is comparatively larger, whereas range of our head widths or head circumference is not that wide. Hence the scale or variance of the individual variable is important. So whenever we see any difference, we need to make sure that we scale that difference by some sort of variability of that difference. Hence, every test in statistics is defined in this format. Any test of significance of difference is defined in this format. So the actual value of the difference divided by variability of the difference. So we can see whether this difference is actually statistically significant. So let me first go for test for proportions. Here is one example. CEO of a large electric utility claims that more than 80% of his 1 lakh customers, 10 lakh, so 1 million customers are very satisfied with the service that they receive. test this claim, the local newspaper surveyed 100 customers, because you can't actually go and survey all 10 million 1 million customers. So the newspaper surveyed 100 customers, and out of them 86 customers say that they are very happy. Okay, so now using this data, we want to check whether the CEO's claim is correct. CEO is claiming that at least 80% of my customers are very happy. Okay, what happens in this particular sample? So we want to claim whether P is greater than 0.8. So that is my hypothesis of interest. So we would take null hypothesis to be P equal to 0.8 and an alternative hypothesis as P greater than 0.8. Okay, because my interest is in proving that P is greater than 0.8. Now what is the sample proportion? Sample proportion is 86 upon 100. So it is 0.86. So at least as a value 0.86 is larger than 0.8. But again, as I said, it may be that okay, we got lucky and we got 86 in this particular sample, but some other sample might actually turn up to give me only say 75 people who are happy. So we want to make sure that this 86% is not occurring due to chance. So this is how the test statistic looks like. Okay, so P hat minus P naught. P naught is my value of interest, that is 0.8. P hat is the value that we observe, that is 0.86. So we want to check whether this difference 0.86 minus 0.8, which will be 0.06, is it significant. So we need to scale it by its standard deviation, standard error. Okay, so the formula is P naught into 1 minus P naught divided by n in square root. Okay, so it turns out that this particular ratio turns out to be 1.5, and we have seen in normal table that okay, if I get this value as 1.5, then I want to see what is the probability of getting value 1.5 from standard normal table, 1.5 or larger than 1.5 in magnitude. So to the right of 1.5 and to the left of minus 1.5. So it turns out to be 0.067, which means that this p value is greater than 0.05. So in such case, we do not reject our null hypothesis. So we say that we cannot say that that more than 80% customers are happy. Okay, so even though in the present sample 86 customers are happy out of 100, in general this may be occurring purely due to chance. So we cannot really claim that overall more than 80% of my customers are happy. Okay, now here is another example. In order to quantify the respondents' satisfaction with the washing result, they were asked, are you generally satisfied or dissatisfied with the washing result of your laundry? Okay, and they were asked to give their answers on 5-point scale, where 5 means very satisfied, 4 means somewhat satisfied, 3 is neither satisfied nor dissatisfied, 2 is somewhat dissatisfied, and 1 is very dissatisfied. Okay, so these are the proportions. So for liquid detergents, out of 1832 people who were asked this question, 503 people reported that they are very satisfied, whereas for powder detergent, out of 1623 people, 542 reported that they are very satisfied. So the percentage of people who are very happy, so for liquid detergent it is 27%, for powder detergent it is 33%. So now we would like to see whether the satisfaction levels are different for these two types of products, liquid detergent and powder detergent. As of now in the current sample, that seems to be the case. Okay, 27% people said that the liquid detergent with liquid detergent they are happy, 33% say with powder detergent they are happy. So we can see that in the present sample there is a gap of 6%, but we need to check whether this gap of 6% is actually significant, means is there really a gap, or is it occurring just by coincidence in this particular sample. So my hypothesis of interest is proportion of customers satisfied with powder detergent is not equal to the proportion of customers satisfied with liquid detergent. Okay. So my null hypothesis is always in terms of equality, and alternative hypothesis is P1 not equal to P2. Okay, that is P1 minus P2 is not equal to 0. So I compute this difference. The difference is minus 0.06. How do I get this Z value? So the Z value is my test statistic value. It comes from this formula. So P1 hat minus P2 hat. P1 hat is 0.27. P2 hat is 0.33. So this is 0.06 minus. I want to check whether the difference is 0. So we use 0 here. And then N1, N2 are the number of people in each group. So my N1 is 1832. N2 is 1623. And what is P1 hat star? Sorry, P hat star. P hat star is basically a pooled estimate of P1, P2. So what's a pooled estimate? So we compute overall proportion. X1 is this 503, X2 is this, N1 is this, N2 is this. So we compute X1 plus X2 divided by N1 plus N2. Okay, X1 plus X2 divided by N1 plus N2. And if we compute this, then we get the value to be minus 3.79. And we know that for normal distribution, anything beyond 1.96 is not accepted. So as soon as you get 1.96, we say we should reject H0. So minus 3.79 is beyond 1.96. So we reject H0. Okay. And this actually turns out to be the confidence interval for the difference. And we can see that 0 does not belong to this confidence interval. The confidence interval is completely to the left of 0, minus 0.09 to minus 0.03, which means that 0 is not an acceptable value of the difference. So we will conclude that the proportion of people who are very satisfied due to powder detergent is different than the proportion of people who are very satisfied due to liquid detergent. Is it okay? So this was a test for difference between proportions. Now we go for test for means. Sample weights of detergent powder in a 100-gram pack are given below. These are some weights. If the weights are below 100 gram, then of course customers would complain. If the weights are consistently above 100 gram, then company cannot afford, because you cannot charge for 100 gram and give more than 100 gram. So hypothesis of interest is to check, is mean weight different than 100 gram? Okay, we are not worried about more or less. We just check whether it is different than 100 gram. So my null hypothesis is mean weight is equal to 100, and alternative hypothesis is mean weight is different than 100. Okay. So what do? We have 15 observations. These are 15 observations. The sample mean turns out to be 100.53, so it is almost close to 100. Standard deviation turns out to be 4.41. So we compute the test statistic as x bar minus mu naught divided by s by root n. So x bar is 100.53, mu naught is the value of interest, that is 100, s is this 4.41, n is 15. And we either compare it with t distribution, but we have not studied t, so you can actually compare this with again 1.96 as the cutoff value. Okay, z statistic. Now this value turns out to be 0.47. Okay, this t value turns out to be 0.47, which is less than 1.96. So we do not reject H0. So we say that mu equal to 100 is an acceptable value. Is it okay? And if I compute the confidence interval, then it turns out to be 98.09 to 102.97, which means that this confidence interval also contains contains 100. Hence 100 is an acceptable value. So this mu equal to 100 is not rejected. Okay. The same can actually be verified in a box plot and an interval plot. So this is a box plot of the data, and this is the observed mean, 100 point something. This is hypothesized mean, that is 100, and we can see that the confidence interval contains 100, so it is an acceptable value. Okay. Now this is another example. Data were obtained from the 40 heaviest men in a scientific study. all weighing at least 100 kg, and their cholesterol measurements were recorded in milligram per 100 milliliter, and behavior type has been categorized into two types. So type A behavior is characterized by urgency, aggression and ambition, while type B behavior is relaxed, non-competitive and less hurried. The question of interest is whether in heavy middle-aged men cholesterol level is related to behavior type. Okay. So we have cholesterol levels for two different types of personality types. We want to see whether the two different types of personalities have different mean cholesterol level. So if we first compute sample mean, for type A it turns out to be 245, for type B it turns out to be 210. These are respective standard deviations. If we draw box plot for type A and type B, we can see that type A people seem to have higher values of cholesterol. We want to see if this is statistically significant difference. Okay. So my test statistic would look like this: x1 bar minus x2 bar minus 0, 0 because we want to check whether this difference is 0, and divided by pooled variance, pooled standard deviation under root 1 by n1 plus 1 by n2. And how do I compute this pooled standard deviation? It is n1 minus 1 s1 square. So s1 is standard deviation of first group, n1 is sample size of first group. So s1 is this, s2 is this. Okay, and n1 n2 are, so here both are 20 20. Okay, I have 20 people in type A, 20 people of type B. So n1 n2 are 20 20. Okay, we compute this, and our hypothesis of interest is mean cholesterol different for two groups, that is mu A not equal to mu B. Hypothesis of interest becomes alternative hypothesis. Null hypothesis is mu A equal to mu B. Okay, so if we compute the difference and confidence interval for the difference, we get confidence interval as 7.3 to 62.2. So 0 does not belong to this confidence interval, so 0 is not an acceptable value. And we can compute the test statistic. It turns out to be 2.56, which is much higher than 1.96, so we reject H naught. So we conclude that yes, the two types of personalities actually have different mean cholesterol levels, significantly different mean cholesterol levels. Okay, sometimes, so here what happened is I had these two groups, and these two groups had no relationship with them, means these were 20 people, these were 20 different people. But sometimes we may have some dependence in these two groups. So here is one example of that type. These data give systolic blood pressures for 10 patients with moderate essential hypertension immediately before and 2 hours after taking a drug, captopril. Okay, so for patient number 1, I have his or her reading before taking the drug and after taking the drug. Similarly for patient number 2, 3, 4, etc. Interest is in investigating the response to drug treatment. So we would like to see if the BP has reduced significantly due to the drug. Now here I should compare BP of first person with his or her own BP, correct? I cannot compute this 210 with this 165. I should compare 210 with 201, 169 with 165, 187 with 166 and so on. Okay, so here these two samples are clearly dependent on each other, so there is a pairing here. Okay, there is a clear pairing. Hence in this situation we carry out paired t-test. Okay, we carry out paired t-test. What is the test statistic? We compute differences D first. Okay, so the differences will be, here it will be 9, here it will be 4, then 11 and so on. D bar is the mean of the differences, and we want to check whether the hypothesized difference is 0. So D bar minus 0 divided by standard deviation of the differences upon root n. N is number of people, so, or number of observations. So here I have 10 people, so n is 10. And if we compute this, so hypothesis of interest is, does captopril reduce the systolic blood pressure? So the blood pressure before taking the drug, is it greater than average blood pressure after taking the drug? Okay, mu B greater than mu A, and our null hypothesis is mu B equal to mu A. So we compute this and it turns out that the test statistic value is 5.4, which is much higher than 1.96. So we reject H naught. Okay. We can see this in the box plot also, that my interval is somewhere here, whereas hypothesized value 0 is very far away from the interval. Okay. So these are some of the examples where we used test for difference between proportions, test for single proportion, test for single mean, test for two independent means, and test for paired means. Okay. So these were simple tests. There are extensions where you can have more than 2 samples, etc., but we will stop at the 2 sample tests only. Thank you.